Good morning. Now we are going to look at the last section of mechanics, which is uniform circular motion. The first point in the syllabus says that we need to draw a vector diagram to illustrate that the acceleration of a particle moving with constant speed in a circle is directed towards the center of the circle. Okay, I can tell you that at this point A, this object is moving tangentially, in other words, along the tangent to the circle, but it keeps on going in a circle. It keeps on traveling in a circle. The only way that can happen is if there's a force at right angles pushing it towards the center of the circle at every point. And this force is normally provided by the tension of the string or the rope or whatever's keeping it from following the tangent away from the circle. So we have to figure out the centripetal acceleration. At any moment, the velocity is at a tangent to the circular path. In other words, if this force were to be released at any point, the object would carry on in that constant velocity. So it would carry on moving along that tangent in that direction where it is going at that time. The direction of the net force, this centripetal force, is perpendicular to the circular path. The way we look at this is that we can take 2 points around the circle. This is at this point here, then at this point here. At point A, it is travelling at velocity v1. At point B, which is not labelled, it is travelling at v2. The speed is the same, but the velocity is different because it has a different direction. Velocity is a vector. So, we look at the definition of acceleration. What is acceleration? It's the rate of change of velocity. In other words, final velocity minus initial velocity divided by time. Now we can represent these two as vectors. So this is v2, which is this value here, minus v1. Now v1 is going in this direction, so negative v1 is going in the opposite direction. So negative v1 is going downwards like this. So v2 plus negative v1 basically goes from here to here. So I'll draw that there. So this is the resultant vector of v2 minus v1, or rather v2 plus negative v1 gives a vector in that direction. So this green vector here is the difference of v1 and v2. So this is a resultant of v2 minus v1. All we need to do is divide by t, so it changes by a factor of t, and that is acceleration. Notice that we're on this side of the circle, and v2 minus v1 is towards the center of the circle. It's to the left. So at this point it's been accelerated to the left. So that's why the acceleration is in that direction. If by doing a vector analysis, a graphical vector analysis, you can see that v2 minus v1 will be at right angles to v2 at that point. Body moving at constant speed in a circular path experience an acceleration directed towards the center of the circle. We know there's acceleration because the velocity is changing. If the velocity is changing because of the direction is changing, therefore it must be experiencing an acceleration. Rate of change of velocity is acceleration. This acceleration is called centripetal or centripetal acceleration and is provided by a centripetal force. Now, the centripetal force is not a force in its own right. It's not like reaction or weight or any other force that we've able to label. It's an unbalanced force. So when you've considered all these other forces such as weight, reaction, friction and so on, the sum of these forces, if the force acts at right angles to the motion of an object, then it will make it travel in a circle, and therefore it will be called a centripetal force. For example, the component of tension in a string that we can look at. Centripetal force, by the way, does not change the kinetic energy of the body. It doesn't make the body speed up because it's acting at 90 degrees to the direction of motion. If it acted in the same direction as the motion, A, it wouldn't be centripetal, and B, it would provide kinetic energy to the object. So it's always at right angles. Here we have a cyclist on a flat surface. The reaction is acting upwards, the weight is acting downwards. Vertically, there's no acceleration, so reaction must be equal to mg. But there's an unbalanced force acting to the left, which makes him travel in a circle. So vertically, the forces are balanced. We know that the reaction is equal to the weight. Horizontally, there's an unbalanced force acting in this direction at right angles to his motion, so this is a centripetal force which makes him travel in a circle. And what is the point here? Why is there a force there? Because it's provided by the friction between the tyre and the road. If there were no friction, he would slip. Here we have an inclined plane. The weight is always acting downwards. R is acting now perpendicular to the banked road surface. R mg does not equal R anymore, but it does equal to the vertical component of R, because it's not accelerating up or down here. So vertically, we know the forces must be balanced. mg, which is the weight, is equal to R cosine theta, which is the vertical component of R. Use the trigonometry to show that the vertical component of R is going to be R cos theta. Horizontally, the only force that's acting here, if there's no friction, is the horizontal component of R, which is that size there. So this is going to be R sine theta, which pushes the bike that way. That makes him travel in a circle. This provides a centripetal force, which is mv squared over R. So if we combine R2 and R1, we end up with tangent of theta is equal to v squared over rg. You could try to prove that. Apply the expression for centripetal acceleration. It depends on the velocity of the body, depends on the radius of curvature of the path. This is the equation we need to know. A is equal to v squared divided by r. In a Bond film, Blofeld puts Bond sitting inside a rotating cylinder. It spins faster and faster until it reaches a constant rotation. The radius is 4 meters. It travels 2 rotations per second. So you know from 2 pi r what the distance is in one rotation, so you can find out how many rotations he does, which is 2 times by 2 pi r in 1 second. Then and the velocity, you square it, divided by 4, and gives the acceleration. It ends up being quite a high value, and he would die because because that's what Blofeld tries to do. He says, I expect you to die, Mr. Bond. That's what happens in the film. He doesn't die, of course, but anyway, yeah. If he stayed in there, he would die because the acceleration would be too much for him. But you can calculate that. Well, he escapes, but he would die if he stayed in there. Now, this is a little bit of a problem. The swinging bucket round the head thing, yes. Okay, we have a bucket. This is a bucket here, which has been a bucket of water doing the loop, which you've seen before. There are 2 forces acting on it when it's at the top of the swing. The weight is pulling down, because the weight is always down. The tension in the string holding the bucket, or the arm pulling the bucket down, is a second force. So we have 2 forces that are acting down: the weight and the tension in the string. Notice they add up in the same direction, so we can say that the tension plus the weight will give the acceleration. We know it's acceleration because the velocity is changing. This is the unbalanced force. This will be the centripetal force because it's the resultant force. T plus mg gives an unbalanced force of ma. Newton's second law will cause an acceleration. This will be the centripetal acceleration. How about if it's at the bottom of the swing? We know that weight is always acting downwards, but it's being held up by the arm or the string or the rope or whatever. So there's a force upwards, which is the tension. Now we know they're in opposite directions now. So tension is acting up, and the weight is acting downwards. Which way is acceleration? Well, the acceleration is always towards the centre of the circle, so it's in the direction of the tension. So we can say that the unbalanced force, F is equal to ma, is equal to t, upwards, because the acceleration is upwards, minus mg, because mg is downwards. We combine these together. How could we rearrange this to find out what the acceleration would be? What happens to the tension if the speed is staying constant? If the speed is constant, the acceleration is going to be constant. What will happen to the tension? Well, here we know that the acceleration, ma, is going to be constant. Tension here will be less than the tension here, I think. Here we have some kind of pendulum, like a rotating pendulum. Vertically, the forces are equal. mg is equal to the vertical component of the tension, which is t cos 30. mg is equal to t cos 30. Horizontally, however, there's an unbalanced force which is making this go in a circle. It's this unbalanced force, because it makes things go in a circle, is a centripetal force. And that's equal to the horizontal component of the tension. So t sine theta is equal to the centripetal force, which is mv squared over r. Divide this equation by this equation, we end up with tan theta is equal to mv squared over mgr, which simplifies to v squared over gr.